I'm going to use a technique that I use for lectures during COVID. And after that, whenever I was out of town for some research trip, I had to give a lecture remotely, or if there was a snow day. Snow days aren't what they used to be. We used to have the day off. Now we lecture online. So this is the bonus episode for February. We've made some jewelry boxes in the shape, looking down at them, some regular polygons. So we made, a jewelry box that has the shape of an equilateral triangle. So that's the shape of three sides. All three sides are the same length. We made one in the shape of a square, right? That is a polygon with four sides, each of which has the same length. And these shapes are unique given the number of sides. And this is a sort of an interesting statement in the sense that, I can consider this triangle, and I can draw another equilateral triangle over here, and I can draw, bigger one over here, and maybe a tiny one, and an even tinier one here. And I get to say all of these have the same shape. Of course, 1, 2, 3, 4, 5, those are 5 different triangles. But if I'm allowed to take them and translate them, that means move them and rotate them and scale them, then I can make them all look exactly the same. So that's what we mean by the same shape, even though the triangles themselves are different triangles. And once you say it's a regular polygon with the number of sides, then you've determined it uniquely, the shape uniquely. And you're quite familiar with the small number of side polygons. Well, we've got the triangle and the square already, right? There's the, let's see if I can do this. There's the 5-sided one, the pentagon. There's the 6-sided one, it's just the hexagon. And then you probably stop, thinking past there. Of course, there's the octagon. Let's see if I can do that one. The 8-sided one, because it's a stop sign. And then otherwise, you don't really, know them by name. They're not familiar objects. And there's a reason for that. Okay, one of the reasons is some of these small n, say n for the number of sides, shapes have some interesting properties. So, for instance, if you wanted to tile the plane, so that means cover all of two-dimensional space with a particular shape, and it has to be a regular polygon. Then there's only a few that work, right? There's the triangle. You can, do the triangles, and then you can, have the same thing going on up here, and you can keep going, and you can take this triangular shape, and you can cover, everything with that shape, leaving no space uncovered. That's what it means by tiling. You can also, of course, do the same thing with squares. And you can also do it with hexagons. Okay, my hexagons are a little woozy, but now you can see like a honeycomb pattern. You can also cover the plane without any space left open with just that shape. There's some interesting properties about the hexagon, which is if you wanted to cover the plane with a shape that uses the least amount of ink, let's say, per area, then the hexagon is the shape that does that. The other thing I guess I can say is 1, 2, 3. These are the only regular polygons, triangles, squares, and hexagons that do tile the plane. There's no other shape that can do that. No other regular polygon that can do that. Now, if you're interested in tiling, further interest, you should check out something called Penrose tiling, which is a really fascinating set of shapes that can tile the plane. So they're not regular polygons; they're different shapes, where the tiling is not periodic in any way. Okay, so we've got these basic shapes. And let's think now in terms of our crafting, right? What if we wanted to make these shapes? Well, we already saw in the construction video, but I'll reproduce it here. We wanted to make an equilateral triangle with the side lengths of that size. Well, we could either, measure with a protractor an angle of 60 degrees, 60 degrees here, right? And then draw out, that length, and then we'd have an equilateral triangle. The way we did it in the video, it's inherently a little bit more accurate, a little less prone to error, is we took our compass and set it to that length, put the sharp end here and drew a arc of a circle, and the same thing here, drew the arc of a circle, and where they met, that's the point which makes the third point on the triangle, and then you just draw with your ruler the places in. Of course, if I go to the square, right, that's easy. Then these are, 90 degrees angles. Well, that's kind of an interesting question for the pentagon. Let's see if I can do a better pentagon than I did before. If I draw a pentagon, okay, well, what angle is that? Well, I'm not going to show you the angle of the pentagon. I'm going to show you the angle that you would need for any regular shape. There's an easy proof of that. And then, well, I can go to the hexagon. Let's see if I can draw a good hexagon. These angles are 120 degrees. And the way you can see that is if you fill in the pentagon with a point to the center, then these are all equilateral triangles. And so this is 60 degrees. This is 60 degrees. And so then the big angle, right, is just the sum of those two is 120. Again, I'm going to come back and show you a way to figure out what angle would be for any of these shapes. But before that, and it'll lead into the construction, I want to have a way to generate these shapes in a movie that I'll use a computational tool for. And I don't want the same length of sides, because as the number of sides gets bigger, then the shapes get bigger, and then they're harder to compare. So I'm going to cram all of the shapes into the circle of radius 1. In math terms, we call this the unit circle. Okay, so pretend that's a well-drawn circle, and here's the center. Now, what I'm going to do, for instance, to draw the equilateral triangle that sits inside the unit circle is I'm going to divide the 360 degrees of the circle into 3 pieces. So each of these will be 120 degrees, 360 divided by 3. I'm going to put the vertices of my equilateral triangle here, right? And then, oh, there you go. There's the equilateral triangle. Okay, it doesn't look very equilateral, but have some sympathy for me and my drawing skills. And now I'm going to take a little break. We're going to go to a video where I'm going to do the same construction for n increasing. Of course, we'll start at 3. Okay, here we are starting with 3. We're going to go slowly up, 4, 5, and now it's going to start going faster. And now you're going to see why these larger n shapes are kind of aesthetically uninteresting, because they start to look more and more like a circle. Okay, let's go with the calculation of what angle the polygon with n sides has inside. So we know that if we've got a polygon with 3 sides, that the angle is 60 degrees. Well, let's just take as a basic fact that if I've got any triangle, that when I add up the 3 interior angles, I always add up to 180 degrees. So now let's think of our construction of the n-sided polygon inside the unit circle. And let's just think about this for a minute. I'm going to have 2 sides here. Okay. And I'm imagining this is going to be for any n. But, I've cut n fairly small looking so that I can see something. And one thing I do know is that to make the side with any n, I do this construction in the unit circle, right, where this angle is the 360 degrees, divided into n pieces. So that angle will be 360 degrees divided by n. Right, and then I also know that this is the angle I want here. Right, I'm going to call that angle theta. This is what we want to know for the inside of polygon, what that angle is. We know what it is for the triangle, the square, and the hexagon, but now we want a more general formula. And I know, though, that if I look at this triangle, right, I have half of theta, that's this piece here. And then if I add half of that one, and then I add the 360 degrees divided by n, then I have to get 180 degrees. Okay. So that tells me that, well, this just gives me n, this just gives me theta, plus 360 degrees divided by n is 180 degrees. Or I can write this, because theta is what I want. I'm going to have theta is equal to 180 degrees minus 360 degrees divided by n. Now, there's a couple of things I can see right away, right? Well, this is the formula. So I could put in n equals 5, and I'll figure out what angle comes out of that. But even though I'm a mathematician, I'm not very good at arithmetic. So I'm going to just leave this formula. And you can plug in n equals 5 and see what angle comes out. And you can check on Google, because I'm sure Google will tell you what the interior angle of a regular pentagon is. But there are a few things that I can do. I can just check, I can check some n's, right? I know n equals 3 and 4 and 6. I can just check. So if I put in n equals 3 into this formula, right, then I get 360 divided by 3, that's 120. 180 minus 120, that is 60 degrees. Okay, so check. Now, it seems like we proved this formula, so, and that it works for every n. Why am I checking just to make sure? Sometimes you make mistakes, with algebra, and this is just a way to verify. I can put in the n equals 4. That gives me 180 degrees minus 90. That's 90 degrees. Okay, that looks good. And I can put in my n equals 6. That gives me my 120 degrees. Right? So these things are just checks, right? But it gives you more confidence in this formula, by the way, which is indeed correct. There's another thing that I wanted to point out, and that is we can look at, at the limit as n, gets, large. If n gets really large, right, then I'm looking at interior angles that are getting closer and closer to 180 degrees, right? Because I'm subtracting something that's smaller and smaller and is getting bigger and bigger. If you have had any calculus or destined to have some calculus in your future, this is a limit process. You're looking at the limit as n gets larger and larger, limit as n goes to infinity, and in that limit, this interior angle goes to 180 degrees, which is why, right, these shapes, that's another way to see why these shapes for large n look more and more like a circle, right, where you could sort of see like these things are basically flat here. So interior angles of 180 degrees. Okay, maybe I should try and work out the n equals 5, 1. Okay, let's see. If I take 360 degrees and divide by 5, I'm going to say that's 72. So that's theta is 180 degrees minus 72 degrees, which should be 108 degrees. And I'm going to just go and check and make sure that's right before posting this video. Again, I'm a mathematician. Arithmetic is not my strong suit. I know that must seem strange to some of you.